Want to know how to design a synchronous or asynchronous counter? So then this lecture is for you guys. So in this lecture we will be going through each concept of what is synchronous counter, what is asynchronous counter, what are the benefits behind this, and how we can configure and design those things also. So let's first see what will be the quite difference between synchronous counter and asynchronous counter. So in synchronous counter, the clock will be simultaneously applied to all the flip-flop as we saw previously, right? So in the registers and other things as we have seen, the clock will be connected to all the things as. So that is will be synchronous thing. In asynchronous thing, the clock will be connected to first one only. So here you see the clock is connected to first flip-flop only. So rest are connected with the previous input or nearby flip-flops output. So this is called asynchronous counter. So synchronous counter will be faster in operation, whereas asynchronous counter will be slower in operation. So the synchronous counter can count any random sequence, so like from 0 to 3, 3 to 5, 5 to 7, like that way it can count. But asynchronous counter will be always a sequence counter. So means that either that will be up counter 0, 1, 2, 3 like that, or it will down counter like 3, 2, 1, 0 like that way only. So here we are going to see mod 8 up counter structure. So here the counter is configured like this way. So where we have taken a JK flip flop. So many of the time we take a counter to design JK with the help of JK flip flop only. So when both the J and K input is 1, so when the clock is applied, the output will be toggling from the previous state. So let's taking this into advantage. So let's get into that thing how this will work as a up counter. So let's take initial condition that is 0 0 0. So, okay, so this is the thing. So as we know, both on all the flip flop J and K inputs are 1. So when here you see J0 J1 JK, but here we are taking in the format of Q2 Q1 Q0. There is a quite difference. So the output can be taken in any format that is based upon our thing only. So we can design any kind of things like this way. So if the question asked to analyze this with Q0, Q2, Q1, then you can analyze like that way also. That is our wish. So we can do it in any order because this is a counter. So all the transition bit will be giving the same results only. So that will not be a problem. So when we apply the first clock, so here both the input are 1. So previous input will be toggling. So here Q0 only will toggle for each cases because the clock is applied to that only directly. So Q0 will change all the time. So 1, then at the clock 2 it will be changing to 0, then it will be changing to 1. So like that way it will be keep on changing. So at the 4th clock it will be 0, 5th clock 1, 6th clock 0, 7th clock it will be 1, 8th clock it will be 0, and 9th clock it will be 1. So here if you see, we have connected the Q0 output as a clock to the next state of a flip flop. You see, and bubble is there. So the bubble is naming that as a negative edge trigger. Okay, so this is a negative edge trigger flip flop. So negative edge trigger. So I will let you know what are the different ways to configure up and down counter with all the things. So I will discuss that next. So for now, note it that is a negative edge trigger because of this bubble. So whenever there is a transition from 1 to 0, the state of this flip flop will be changing. So whenever the Q0 output is changing from this state to this state, the Q1 output will be changing. So here if you see, so here the 0 to 1 it is changing. So this is an up conversion. So this state will not change. So this will be 0. So here also this is changing from 0 to 0. So here also it won't be changing. But here if you see, which is changing from 1 to 0, then this output will be toggling. So this will be 1. So here if you see 0 to 1, so this is an up conversion. So here it won't change. So previous input maintains as it is. So the thing is that whenever there is a flip from 1 to 0, the output changes. Here you see it's get toggle. So here there is an up conversion. So this input won't change. So here it is same. So this also won't change. So here if you see, this is changing from 1 to 0. So this input will be flipping. So here you see it is changing from 1 to 0. So this input will be changed to toggle. So this is 1 0. I hope you guys getting right. So whenever there is an, this will act immediately because if you see whenever this changes, the input will be readily available. So 1 to 0 will be available. So 0 will come immediately. This transition will change. So that is how it will work. Okay, because we are getting the output after end of this clock pulse. So once this clock is given, so we will be wait for a few seconds and we will observe what are the changes observing. So that is what the counter will work. Okay, so please pause the video and try to complete all the boxes before I am completing. So that will be a good practice for you guys. So here 0 to 1, so no transition, it will be maintaining 0. So 0 0 no transition, that will also maintain as it is. Here there is an 1 to 0 transition, so it will coming to 1. So here also there is an 1 to 0, so here also it will be 1. So 7 7 this also will be 1 and 1, so because 1 and this will maintain same. So it will be 0 and this will be 0 and this will be 0 0. Okay, so here if you see 0 1 2 3 4 5 6 7, so you see this is a counting from the state. So this is an up counter, so it is counting from 0 to 7. So that is why we have stated this as a mod 8. So 8 level of things that is counting from 0 to 7. So this is how the up counter will work. Okay, so I hope you guys able to understand. So here how the frequencies can be modified. So here if you see the q naught output will be, so this is the q naught, right? So this input is changing only two states, so this output will be f clock divided by 2. But if you think that this state, here there is a transition one time, so here transition one time, third time and fourth time, so four times it is transition. So this clock pulse will be fc divided by 4. So it's not a clock pulse, the frequency of change in the output here. So here if you see there is only two transition at a q2. What's happening at a q2, it will be changing at a level of 8. So if you see, we can consider, we should not consider this way, so we can consider the flip flop counts to be changing accordingly. So here it is 2, here it is 4, here it will be changing by 8. So if we map this into an real time output, then you guys can able to visualize these things. So q0 will be fc by 2, so q1 will be fc by 4, qc will be fe by 2. Okay, so this is what the change of things that we can take. So or else you guys can even remember like this. So q0 is only one bit, so one bit can change up to two levels only, so that is 2. So when we include q1 and q2, there is 2 bit and 2 bit having 4 level, so that is fc divided by 4. So when we include q2, there is a 3 bit having 8 level, so that is changing to fc by 8. Okay, so I hope you guys are able to get it right. So this is how the transition will happen here. So this frequency calculation at each level will also be important, so please make a note of it also. So let us now discuss how the mod 8 up down counter can be designed. So mod 8 down counter. So similar to up counter, there is a quite small difference only will be there. So let me draw that. Shall I able to copy it? So let me erase and copy paste there. Okay. So here see the clock will be connected without bubble. So there we are connected with a bubble. So here there is no bubbles. So that is what the difference between down and up counter. So I hope you guys able to understand things. So let us directly solve this one. So you guys will be able to see the up counter. So here this is the mod 8 down counter. Okay. So let us similarly discuss how the things will come. So let me draw a table. So here clock the same Q2, Q1, Q0. So 0 it will be 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So let's take up to 9 clock. So the same thing, but whenever there is a transition from 1 to 0, this will be changing because this is a positive edge trigger. So the required difference is negative edge trigger and positive edge trigger. The simple, so based upon the clock movement, you can see now that is completely, the counter is behaving completely different. So that is what the thing that we can need to explore in the digital things. So here if you see, when Q0 is applied, so this output will be toggle. So here because this is changed from 0 to 1, this output will be toggle, so this output will also be toggle. So now if you see, this is starting from 0 and then it's going to 7. So this is a down counter. You can clearly resemble from two stages itself. So let me further continue. So this output will be toggling to 0. So this won't change because this is negatively triggered, right? So this will remain same. So this will remain same. So this will change from 1 to 0. Let me draw it here. So this will change from it will be toggle at every level. So here you see there is a transition from positive. So this will be flipped. So here it will retain same. So like that way only we have to fill rest of the state. So 1 0 0. You can clearly state this is 0 5. So this will be 4. Next will be 3. So that will be 0 1 1. So next will be 2. So 0 1 0. And next will be 0 0 1. And 8 1 will be 0 0 0. Then again it will go to 1 1 1. So here you see. So it is counting from 7 to 0. So this is a down counter. Okay. So this is how we will be designing the up and down counter everything. So here is a shortcut guys. So this is the thing that you have to remember. So type of trigger, clock input, counter. Okay, so whenever there is a positive edge trigger and negative edge trigger, positive edge trigger, negative edge trigger. So if the clock is q q bar q bar, so the similar thing, so we have took the things right. So whenever we have a positive clock pulse, the clock pulse is connected as a positive without any bubble, and the next state, so here if you see the q is connected. So if the positive edge trigger and q is taken, then this is down counter. The example is this one. So here you see there's a clock is positive and q is connected. If they take negative and q is taken, so this is an up counter. This example is this one. So here we see the clock is toggled and the q is taken. So this is the two thing. So if positive trigger and q bar is taken, then this will be an up counter. So here the clock is positive, but instead of q, if we connect the q bar as here, then that will be acting as a up counter. So then negative and negative means this is a down counter. Okay, so this is the shortcut to remember, but I will be suggesting one more shortcut. So take this as 1. So positive means 1 and q means 1. So negative means 0, q means 1. So negative positive 0, positive means 1, q bar means 0. Okay, so negative means 0, negative q bar is 0. So 1 XOR 1, that is 0. So 0 means down counter. So 0 XOR 1, that is 1. So 1 means up counter. So 1 XOR 0, that is up counter. So 0 XOR 0, that is 0. Okay, so this is similar to XOR truth table, XOR not XNOR. So XOR truth table. So this is a shortcut, guys. So you guys can remember and you guys can solve any kind of 1 marks very easily. Okay, so there is one more things. So delay in asynchronous counter. So because we have already clearly stated, so whenever there is a clock transition happen, we need to wait for some time and we need to get all the output. So let's take how much delay that will happen in a asynchronous counter. So don't confuse, guys. So once the clock is triggered, we need to wait for all the states to change, then only we have to take the output. So that may confuse you guys. So the total delay which will be equal to, so delay and assets are very important, so please make a note of it. So n number of flip-flops to that of propagation delay of each flip-flop. So n is number of bit and propagation delay of each flip-flops. Okay, so then the t clock, the t clock will be, or this need to be much greater than the ntpd, because this is this much delay. For an example, this is 30 milliseconds, 30 nanoseconds. Okay, so the clock pulse need to be greater than this. For an example, this need to be 40 nanosecond. Then only we will be able to observe all the state transition that is happening in the particular 3 or 4 flip-flops. If the clock is triggered before this one, then before the counters are getting triggered or changed to a new state, the next clock will be triggered. So that will be collapsing the entire circuit. Then we may not get our desired counter. So the condition is that the t clock pulse should be much greater than the total delay. So this is one very important thing, guys. So please make a note of it. Plenty of questions I have already asked. Even 2025 they have asked one question resemble. 2023 also they asked on 2 mark here. So let's calculate f clock. So f clock is nothing but an inverse. So that will be 1 less than TPD. So this one. So f max. Now f max which will be equal to 1 divided by ntpd. So the question they ask is this one. What will be the f max if the propagation delay is like this? So they haven't asked this much directly. So they have hinted and twisted in anywhere. So like that way only we need to find out how the delay and how the things will work there. So I hope you guys will be able to understand few things, how we can design counters and everything. So this much only, counters having not have that much important. It's important in gate purpose perspective, but this much only. So there is nothing more than to ask here. So in next class, let's discuss how we can analyze and create a synchronous counter. So that we will be discussing in next class. So please stay tuned, guys. Like, share, and subscribe the channel. Thank you, guys.